Imagine you're just, staring at a medical chart, and a doctor has written out a standard dose of medication for a patient.
Right.
But there is this tiny, almost invisible smudge of ink near the number, like a dot no bigger than a grain of sand.
Oh, wow.
And because of that single misplaced speck of ink, a completely routine prescription suddenly becomes a lethal tenfold overdose.
Which is terrifying.
It really is. I mean, when we deal with numbers in our daily lives, we expect absolute clarity. You count 5 apples, the receipt says $5, you pay, and you move on.
Yeah, but when you start pushing the boundaries of scale,
Mm-hmm.
that simple counting system completely shatters.
Exactly.
It shatters because our brains and our standard way of writing numbers, they just weren't built to handle the extremes of reality.
Right, like the really massive or the really microscopic.
Exactly. Whether you are dealing with the unfathomable size of the known universe or just the microscopic concentration of a drug in a patient's bloodstream, standard numbers become this visual landscape that is dangerously unreadable.
Which is exactly why we are wading into these mathematical muddy waters today. We are doing a deep dive into the hidden language of the very big and the very small.
Scientific notation.
Yes, scientific notation. So if you're prepping for the TEAS or HESI nursing entrance exams, you need to consider this deep dive mission critical.
Definitely.
But honestly, even if you are just insanely curious, this is about understanding how professionals separate how big a number is from how precise it is.
Because messing that up doesn't just lose you points on a test.
No, it can, and it literally has crashed multi-million-dollar spaceships into Mars.
It's true. And to really grasp how this engine works, we need to avoid just, memorizing the modern textbook rules.
Right, because rules are just rules until you know the why.
Exactly. The rules only make sense when you understand why human beings were forced to invent this system in the first place. I mean, this wasn't one sudden mathematical epiphany.
I always think of scientific notation as this incredible technological mashup. It's a combination of ancient philosophy, 17th century shorthand, and modern hardware limitations.
That's a great way to put it.
Yeah, they just jammed it all together out of sheer necessity. And the story starts way back in 250 BCE with Archimedes.
Right, in a treatise he wrote called The Sand Reckoner. And what's really fascinating here is Archimedes' actual goal.
He wasn't just doing math for fun.
No, he wanted to mathematically prove that he could calculate a number larger than the amount of sand grains it would take to fill the entire universe.
Talk about a massive intellectual flex for a guy living in 250 BCE.
Seriously.
But how does he even start that? Because, I mean, the Greeks didn't have algebra, right?
No algebra at all.
They didn't have zeros, and they used alphabet letters for numbers.
And that was his central problem. The Greek number system basically stopped at what they called a myriad, which is 10,000.
Okay.
Archimedes realized he couldn't count universe-filling sand with just myriads, so he invented a way to stack them.
Stacking them? Like multiplying them together?
Sort of. He started talking about a myriad of myriads, which is 100 million, and then a myriad of myriads of myriads.
Oh, wow.
Yeah, he was essentially building an early exponential system.
Just to count sand.
Just to count sand. And by doing this, he estimated the universe-filling sand count at something close to what we would write today as a 1 followed by 63 zeros.
That is just wild. He was doing order of magnitude thinking 2 millennia before anyone had the notation to write it down cleanly.
He really was.
Which brings us to the next piece of this mashup, which is René Descartes in 1637.
Right, because Archimedes had the grand concept of stacking magnitudes, but Descartes gave us the shorthand we actually use.
He's the one who introduced the superscript, right?
Exactly, writing the little floating 2 or 3 at the top of a letter to mean squared or cubed.
Because before Descartes, if you wanted to express a big power, you literally had to write out x times x times x times x until your hand cramped.
It was incredibly tedious. So Descartes' shorthand laid the visual foundation. But then you have John Napier in 1614 who invented logarithms.
Wait, logarithms. Let me push back on that a second, because for a lot of people listening, logarithms are just like high school math trauma.
That is a very fair point.
How do they actually help compress these giant numbers?
Well, a logarithm fundamentally answers a simple question. It asks, what power do I need to raise my base to get this target number?
Oh, okay, I'm with you.
Napier's work was revolutionary because it allowed mathematicians to turn complex multiplication into simple addition.
Oh, I see.
That underlying logic is the exact engine that drives how we do math with scientific notation today. But the system as we know it didn't fully lock into place until the 20th century.
Right, because science became deeply globalized, demanding standardization.
Exactly.
We're talking about the International System of Units, the SI units. Suddenly, a physicist in Tokyo and a chemist in London need a consistent way to talk to each other.
And you are measuring the mass of a galaxy and the mass of a single cell using the exact same fundamental metric framework.
It's a huge span.
It is. And then the ultimate modern constraint arrived, which was the early scientific calculator in the 1960s and 70s.
We have the screens.
Yes, you have this tiny LCD screen. You physically cannot fit 30 zeros on a digital display that only has space for 8 or 10 characters.
So hardware limitations forced engineers to standardize a compressed numerical format.
Exactly. They had no choice.
Okay, let's unpack this engine and look under the hood. For you listening, I want to give you a mental analogy that makes the mechanics of this notation click.
I love this analogy.
Think of scientific notation like sorting the mail. Every number written in this format has two distinct parts.
Right.
You have the exponent, which is your zip code. It tells you the massive, broad region, like the sheer magnitude of the number.
Through general area.
Exactly. And then you have the coefficient, which is the exact house number. It gives you the specific, tiny precision within that zip code.
That perfectly illustrates the core standard form. It's a value a multiplied by 10 raised to the power of n.
So A is the house number.
The a is your house number, your precision.
Mm-hmm.
And the 10 to the power n is your zip code, the magnitude.
Got it.
Now, the absolute golden rule for that house number, the coefficient, is that it must be a value between 1 and 10.
Between 1 and 10.
Technically, it can be exactly 1, but it must be strictly less than 10.
But why cap it at 10? I mean, why not let it be 50 or 100?
Uniformity, mostly. If we didn't cap it, I could write a number as 50 times 10 to the second.
Okay.
And you could write it as 5 times 10 to the third. We'd be describing the same amount, but our formats wouldn't match.
Oh, and that defeats the whole purpose of standardization.
Exactly. By forcing the coefficient to be between 1 and 10, there is only one correct way to write any given number in standard scientific notation.
So if I want to write 93 million, I move the decimal point from the far right, jumping it over all the zeros, until exactly one non-zero digit is sitting on the left of it.
Right, you jump it over 7 times.
And I end up with 9.3. And because I moved that decimal 7 spaces to the left, my zip code is 7. 9.3 times 10 to the 7th power.
Yep, that decimal movement dictates everything. If you are dealing with a massive number and move the decimal to the left, your exponent is positive.
Right.
But if you have a tiny fraction, say 0.000045, you have to move the decimal to the right to get a valid house number.
And moving it right makes your exponent negative.
Exactly. So it becomes 4.5 times 10 to the negative fifth.
Okay, so that handles reading and writing. But earlier you mentioned Napier's logarithms turning multiplication into addition. How does doing actual math with these zip codes work?
Well, this is the massive payoff of the system. When you multiply two numbers in scientific notation, you just multiply the coefficients, the house numbers.
Just normal multiplication.
Right, and then you simply add the exponents together.
I always try to visualize the underlying logic here. Why do we just add them?
It goes back to what an exponent actually is.
Right, an exponent is really just a tally of how many times you are multiplying by 10.
Exactly.
So if your first number has 10 to the third, so 3 tens, and your second number has 10 to the fourth, 4 tens.
Yeah.
And you multiply the whole mess together, you just line up all those tens. 3 tens plus 4 tens gives you a tally of 7 tens, 10 to the 7th. You are just counting the tens.
That is exactly the right way to think about it. It turns the multiplication of unwieldy, terrifying numbers into basic arithmetic.
Which is a lifesaver.
It is.
Mm-hmm.
But there is a catch when it comes to adding or subtracting. You cannot simply add two numbers in scientific notation if they have different zip codes.
Ah, so you have to make sure they're in the exact same neighborhood first.
Right.
If one is 10 to the 5th and the other is 10 to the 4th, you have to rewrite one so the exponents match before you can combine the house number.
Exactly. You have to align the decimals, essentially.
That makes intuitive sense. But I want to talk about the ghost in this machine. The hidden gap in the rules that completely blew my mind when I found it in the source notes, 0.
Ah, yes. The zero paradox.
You literally cannot write the number 0 in true scientific notation.
You can't. It is the quiet gap in the definition. And textbooks almost never bring it up.
Why not?
Well, because the rules dictate your coefficient must be at least 1, right?
Great.
And there is absolutely no power of 10 you can multiply by to magically turn a 1 into a 0.
The math physically doesn't work.
It doesn't. The most sophisticated numerical system we have completely blanks on the concept of nothing.
Which is wild.
Ah,
But let's drag this out of theoretical math and into the real world. Because if this notation just lived in textbooks, it wouldn't be a cornerstone of entrance exams like the TEAS or HESI.
absolutely not.
The stakes out here are incredibly high for professionals.
Think about the extremes they deal with. In chemistry, you have Avogadro's number, which is 6.022 times 10 to the 23rd.
That's huge.
Written out longhand. That is 602 sextillion. It's a visual wall of 21 zeros that would make solving a basic equation impossible.
Or take a great mental benchmark we should all keep in our back pocket: the speed of light in a vacuum.
Oh, that's a good one.
It is roughly 3 times 10 to the 8th meters per second. A 3 followed by 8 zeros. 300 million meters every single second.
Fast.
Very. Whenever you see an exponent of 8, you instantly know you are dealing with speeds or distances on a planetary scale.
And then you have the inverse extreme.
Yeah.
The mass of an electron is roughly 9.109 times 10 to the negative 31st kilograms.
Ahead of 31st?
Yeah. In standard decimal form, you're writing 30 zeros before you even hit the first meaningful digit.
And writing 30 zeros isn't just a waste of graphite. It is an open invitation for a human error.
Exactly.
In a physics lab, maybe a typo ruins an afternoon of data. But in the medical field, a typo ruins a life.
This is exactly why nursing programs demand absolute mastery of this. Let's look at a concrete clinical example. A normal adult platelet count runs roughly 150,000 to 450,000 platelets per microliter of blood.
Just to visualize that for you listening, a microliter, which is often written with the Greek letter mu and a capital L, is 1/1,000,000th of a liter.
It's tiny.
Imagine a single tiny grain of coarse sea salt. That rough volume is a microliter.
Now, on a lab printout, those platelet counts don't usually say 150,000. They show up as 1.5 times 10 to the 5th to 4.5 times 10 to the 5th.
Right.
Viral loads, bacterial colony counts, they're routinely reported this way.
So if a nursing student cannot instantly and fluently read those values, they will fail math sections.
Yes.
And more importantly, they will fail reading comprehension questions that quote these lab values directly.
Exactly. The comprehension is key.
Okay, let's unpack this, because this clinical reality connects directly back to that smudge on the prescription pad we talked about at the start.
It really does.
The Institute for Safe Medication Practices, the ISMP, sounds the alarm constantly about how decimals cause fatal errors.
Right. It's the clinical version of what scientific notation is designed to fix: ambiguity in magnitude.
Yes.
The ISMP explicitly bans what they call trailing zeros and naked decimal points.
Right. A trailing zero is when a doctor writes a dose as 1.0 milligram,
Yeah.
and the ISMP says that is incredibly dangerous, because if that decimal point gets smudged, or if a tired nurse reads it during a chaotic night shift, 1.0 looks exactly like 10 milligrams.
Which is a massive problem.
That is a tenfold overdose, all because of one unnecessary zero. The standard is strict. You just write 1 milligram.
And the reverse logic applies to naked decimals. You never write a dose as 0.5 milligram.
Because again, a smudge makes it 5 milligram.
Exactly. You must always lock in the magnitude with a leading zero, so you write 0.5 milligram.
It's entirely about making the order of magnitude unambiguous.
Totally.
Because when magnitude is lost, the results are catastrophic. And that's not just in medicine. Remember the 1999 Mars Climate Orbiter?
Oh, what a disaster that was.
NASA completely lost a multi-million-dollar spacecraft in the Martian atmosphere. Why? Because one engineering team programmed the navigation software using metric newton seconds, while the spacecraft's thrusters were built expecting imperial pound force units.
It resulted in a magnitude mismatch of roughly a factor of 4.45. It is the ultimate cautionary tale for scientists and engineers.
Having incredibly precise digits means absolutely nothing if your broad magnitude and your units aren't tracked with the exact same rigor.
Right. And because these real-world stakes are so severe, exam boards know exactly how to test this.
They prey on the ways human intuition naturally fails when looking at weirdly formatted numbers.
They absolutely do. Instead of just listing off rules, let's look at how our brains trick us here.
Let's do it.
A major intuitive trap involves the negative exponent. A student sees 4 times 10 to the negative third, and their brain automatically links the word negative to a negative value.
I see a minus sign, I think, below 0.
Exactly, but that minus sign is in the zip code, not the house number. A negative exponent just means the number is a tiny microscopic fraction. 10 to the negative third means you divide by 1,000.
So the number is 0.004.
Yes. It is a small, positive number. It is absolutely not negative 4,000s.
Our brains also get tricked by the sheer length of a number. This is a classic optical illusion on multiple choice tests.
Oh, I've seen this one so many times.
You'll see an option like 9.99 times 10 to the third right next to 1.0 times 10 to the fourth.
And human instinct says, look at all those nines. 9.99 takes up more physical space on the page. It must be the heavier, larger number.
But you have to check the zip code first.
Always check the zip code. 10 to the fourth is the 10,000s block.
Yeah.
10 to the third is only the thousands block.
Right.
9,990 is mathematically smaller than 10,000, regardless of how robust that coefficient looks.
Then there's the math trap we talked about earlier. People see a multiplication sign between two scientific notation numbers, and they try to multiply the exponents too.
Which is a huge mistake.
You have to remember the tally rule. You are just counting the tens, so you add the exponents.
Yep.
But my absolute favorite trap, the one that causes pure chaos for anyone staring at a screen during a high-pressure exam, is the calculator E.
Oh, the E.
Wait, so when a calculator spits out 6.02 e to the 3, students actually think the E means raised to the power of.
They absolutely do. They read it as 6.02 raised to the 23rd power.
Oh my gosh.
Which changes the actual value of a number by over 20 orders of magnitude.
That is a staggering error. So where did the E even come from?
It goes back to those hardware limitations we discussed earlier.
The calculators.
Right. Early calculators used 7-segment LCD displays. They physically could not render a small superscript number in the corner.
Right, it was just blocky numbers.
So engineers programmed the capital letter E to stand in for the phrase times 10 to the power of.
So 6.02 E23 is literally just 6.02 times 10 to the 23rd.
Exact.
The E is just a retro visual artifact. If you are taking a digital exam, knowing that translation is non-negotiable.
Overcoming these intuition traps requires a bit of a mindset shift. You have to realize that the formats we are fiercely memorizing for a math test aren't immutable laws of physics.
Right.
They're human tools.
Here's where it gets really interesting. Because depending on what profession you actually go into, the strict rules we just learned can completely change.
They do. We've spent this time talking about normalized scientific notation.
Demanding exactly one non-zero digit before the decimal.
Right. That is the gold standard for mathematicians in U.S. science textbooks. But if you walk into an engineering firm, they use a rival convention.
Engineering notation.
Yes. In engineering notation, the exponent is rigidly restricted. It must always be a multiple of 3.
Why specifically 3?
To perfectly align with the SI metric prefixes we use in everyday life.
Oh, I see.
Kilo means 10 to the 3rd. Mega means 10 to the 6th. Micro is 10 to the negative 6th. They all move in chunks of 3.
So let's say we have the number 93 million. A strict physicist would format that as 9.3 times 10 to the 7th. But an electrical engineer would look at that exact same value, adjust the decimal, and write 93 times 10 to the 6th.
Exactly, because 10 to the 6th translates directly to the prefix mega.
That makes total sense.
If you are reading a schematic, seeing 93 megaohms is infinitely more practical for your brain than deciphering 9.3 times 10 to the 7th ohms.
It proves that mathematical notation is a flexible tool chosen for the task at hand.
It really is.
And just to add one more wrinkle for anyone studying internationally in the UK and much of the Commonwealth, they don't even use the term scientific notation.
Really?
Yeah, they call the exact same system standard form.
Oh, wow. Which is guaranteed to cause panic for an American student searching a British textbook index for the first time.
Absolutely. Okay, if we take a step back and distill the crucial takeaways from you, whether you are prepping for a medical entrance exam or just trying to navigate a world obsessed with extreme data.
Right.
First, relentlessly separate the magnitude from the precision. Keep your zip code and your house number distinct.
Second, remember that a negative exponent just points to a microscopic fraction, not a negative value. Don't let your eyes trick you.
Third, beware the calculator E. It strictly means times 10 to the power of.
And clinically speaking, never, ever use a trailing 0 or a naked decimal when dealing with dosages.
Never. Because, zoom out for a second, this notation isn't just about passing a multiple choice test, it is the underlying invisible logic of modern life.
Think about the headlines you read.
Exactly. A COVID-19 PCR test reports a patient's viral load as being between 10 to the 6th and 10 to the ninth copies per milliliter.
That's scientific notation right there.
And the smartphone you are listening to this deep dive on right now is powered by a semiconductor chip holding roughly 10 to the 11th microscopic transistors.
And when you read a news article about a national budget or a national debt measured in the trillions, you are looking at 10 to the 12th.
Anyone trying to comprehend the sheer scale of the modern world without understanding this notation is essentially flying blind.
You really are. You are stuck trying to count grains of sand one by one when Archimedes already handed us the blueprint for a better way over 2,000 years ago.
I love that.
And if we tie that ancient history right back to the present, I'll leave you with this final thought to mull over.
Okay.
Every single fractional number that a modern computer stores in its memory is saved in a format that computer scientists call floating point.
Floating point.
Under the hood, in the silicon, the processor physically breaks the number into a distinct coefficient and an exponent.
Wait, really?
Yeah, it is scientific notation, translated perfectly into binary zeros and ones.
That is incredible.
The very machines we built to save ourselves from having to do manual math are secretly using the exact same magnitude logic Archimedes invented on a beach in Syracuse, just pulsing at the speed of light.